Good morning, class. So sorry about the big delay getting started. All the laptops were acting funny this morning, but now they're working. So welcome. So today we're gonna try finishing off chapter 3. I want to get started by talking a little bit about tomorrow's little test. So it is in the EX building, which is the other side of College Street. I thought my glitches, as soon as the technologists walk out the door, then it glitches. It is just based on chapter 2. Chapter 1 and chapter 2, I guess, and the materials that we did in practicals that first week. And I'm actually going to have 7 questions that you'll see. And they're all multiple choice, so there's no written part to it. Somebody asked, in the syllabus, it stated that the test is optional. So the question is it optional? I guess this is all about the definition of the word optional. So certainly, it can be worth 5% of your mark in the course. But if your mark on either the term test 1 or term test 2 or the final exam is higher, then that 5% goes to the higher of those 3, highest of those 3. So basically, if you don't show up for a test, you get a 0, but that gets replaced with this other mark. So I think you should, it's sort of like low stakes, right? It's good to come. Even if things go poorly, there's no downside. And then, I may have mentioned I was planning 6, so there's 2 kind of conceptual, really quick little questions, and then 5 that are more, you have to work out a number. I think there should be plenty of time. And definitely bring an aid sheet that has those equations of kinematics from chapter 2, from the summary of chapter 2 that I was writing. I'll do that. So where the actual exact room is now listed on Quarkus, and I can put this in a couple of different places, but this is it. It's based on your last name. And there's the basement, which is EX100. That's a big, big room. Once you get to the room, you can sit anywhere. You just find a table that has a blank sheet. But you do need to go to the correct room. And if you end up in the wrong room when they're collecting signatures, they'll say, you should go to the correct room, and you may have to reseat yourself. So let's give an example. Look at Terry Lee. Which room should they go to? Do you know? So the Lee is the last name because it's the big thing that shows up on the card. So, and HIJKLMNO. So it's L is after K. So they go to EX200. And I can't write on the screen because my HDMI splitter's broken. So we're going to be hand waving. Does it make sense? Lee, EX200, because it's between K and Rod. Gotta know the alphabet. And you have to know your last name. Okay. Don't forget your T-card. We're going to be coming around and collecting your little signature, looking at your T-card. Make sure you kind of look like the person on your T-card. You're allowed a Parker calculator, an aid sheet, and you're allowed a hard copy English translation dictionary as well. And the invigilator might flip through it just to make sure there isn't physics stuff written in there, but that's okay. If you wish to see the first page, I've posted it on the module that's called Mini Term Test. That's where I'm going to be posting the solutions when we're done the test, I guess. It's a picture of stuff that you can have with you. So the other belongings you should not have on your table. There's something, people say you can bring a small plastic bag. These are the same rules that are for final exams, kind of come from the faculty. At the end of the test, when they say the test is done, 6:50, you must stop writing and put down your pen and pencil. Okay. How are we doing with the HDMI splitter? Do you think you got a better one? We could try. I'm going to be writing. I guess we'll do these, and then I have to write a little bit. It's okay to be a little early. I would say always a good strategy with a test, especially a physics or a math test, is to kind of read over the questions first before you really start in on it. Look for the easy ones. And before you really answer anything and fill in a bubble sheet, make sure you've read the problem carefully. And I've heard this from chemistry professors, biology professors. One of the most, probably the most common mistake that students make on these tests is not reading the question carefully. You skim it a little, and then you think to yourself, oh, I know what this is asking, and you answer, but you didn't really read what the question was really asking sometimes. Manage your time, 5 minutes a problem. Okay, and it's really important. You can't have your phone or a smartwatch on you. You can't even be able to see your phone or your smartwatch while you're in a test like this. It's a super important rule at U of T, and it's considered an academic offense if you're checking your phone, or even if you have your phone in your pocket during a test. And you might even forget, right? You might sit down and start writing, and you're not looking at your phone, but then your phone rings in your pocket, and you're caught with a ringing phone during a test or something. That's a trip down to the Office of Student Academic Integrity and about months of delays in your marks and all this stuff. And please try not to get into that situation. Make sure your phone's off and away from you during a test, even the mini test. And smartwatches, obviously. Can't have those either. You're not allowed to be able to communicate with other people except just the invigilator when you raise your hand during a test. Makes sense? No phones. Okay, this is where I want to try writing. So can we try this new HDMI splitter, please? Just give me a second. I wanted to go over this morning's pre-class quiz stuff, so let's unplug this. Thank you. So an object rests on a tabletop. So this is the basic idea of Newton's third law, is that if you have kind of Earth, maybe you've got a book on a tabletop. This is not drawn to scale, obviously, that this is the book. We could call this as 1, and maybe down here, the Earth, or the center of the Earth or something, all the mass of the Earth, is object 2. Then there's this force of gravity, is the force of 2 on 1, because the Earth is the object that is pulling the book. And then there's an equal and opposite force down here, by Newton's third law, of the force of 1 on 2. And the whole Newton's third law is just that 1 on 2 equals negative the force of 2 on 1. They're the same magnitudes, but they're pointing in opposite directions. And that's what's known as an interaction pair, governed by this Newton's third law. And they can't ever cancel each other because they're both acting on different objects. So if you're going to draw a force diagram of the book, you wouldn't draw this force that's on the Earth because that's on a different object. And then this one people did pretty well on. I don't think I'm going to read through those, but these were all true statements. This was the hard one. This one messed up a lot of people. So the sketch, there's two things that you want to do. Step 1 is I draw kind of a sketch, and step 2 is I draw a force diagram. They're a little different, right? So the sketch is just, you have to draw a hand, I guess. Let's call that a hand. And then there's a book. It doesn't have to be artistically beautiful, but that's it. You can even, if you want to, you can label it book. And the whole thing is accelerating upwards. The force diagram, and I'll put here of the book, is just a dot, and then you draw all of the forces that are acting on the book that you can think of. So I would say there's the force of the hand on the book. That's what you're trying to find. And then you've got the downward force of gravity, which is just equal to the mass of the book times g. Makes sense? And then also, it's accelerating upwards. A is equal to 2 meters per second squared upwards. So define, what I'll do here, is plus y equals up. So this is y. So what you would do then is you'd kind of use Newton's second law, a sub y equals the sum of all the forces in the y direction divided by the mass. So that's going to be 1 over the mass times there's an FH on B. Then I would do minus mg. Okay. That's the sum of all the forces. One of them is negative because it's pointing in the downward direction. One of them is positive, so it's actually you're subtracting those two for a vector sum. And then you just want to solve it out, right? So I guess MAY is equal to FH on B minus mg, and then FH on B is equal to MAY plus mg. So it's 3 times 2 plus 3 times 9.8. And you should do those things first. So it's going to be about 6 plus 25. It's around, 29, I guess. It ends up being about 35 newtons. Okay. That's how Newton's second law works. It's sum of all the forces divided by the mass gives you the acceleration, and that's a vector sum. Okay. You people are sweet. I was asking me how I'm feeling. Feeling very well today, 100%. It's just my technology that's ill today. Why are physicists so good at mediating arguments? Because they account for all frames of reference. I don't know. And then, also happy birthday to Grace. If you're going to put on the pre-course survey that's your birthday, it's always the danger you're going to show up on the slides. So, hope that's good. Let's look at this quick little video. And I talked about this a little in the pre-class quiz. It shows you a coffee cup sitting on a dashboard. And so from the inside point of view, if they step on the gas and it falls down. Oh, what force pulled it? But if you look from the outside, the car is going away, and what the drink is doing is almost trying to stay still. It ends up, I guess, getting rotated and falling. And so there is no backwards force on the cup which is going to cause it to fall. That's a fictitious force, I guess. So let me go through this real quickly. Idea here, so a different situation. If you're riding in a car that makes a sudden stop, now your acceleration is backwards, you might feel as if you're kind of thrown forwards into the front of the car. But there really is no such force. Some people talk about fictitious forces, but that's not the way they do it in the Atkina book, and I kind of agree with the author here. It's better to use an inertial reference frame. You do all your calculations and Newton's laws and things in the lab frame, some frame that's not accelerating. And then in that case, there is a backwards force on the passenger that has to cause him to slow down. If there is no backwards force, then the passenger is going to go forward at a constant velocity until there is some backwards force. Make sense? And you can draw it out. If you draw kind of like the system is being the passenger, we'll say the system equals P there. Then what happens is that when you draw these forces, you've got the normal force of the car on the passenger, I guess the seat holding them up. You've got the gravity force, which we call Earth on the passenger, which is going to be equal to mg, down, right? And then, since he's slowing down, the acceleration is backwards, there's an unbalanced backwards force of the car somehow on the passenger to slow the passenger down. And this is probably some kind of normal force, like maybe the airbag or something. Okay. Let's do this one, because we did actually talk about this last time. So if we have a tennis ball, like this one, and it's thrown up, then when it's in the air, there's, or when it's, when it's at rest in my hand, I've got an upward force on it, which is keeping it at rest. When I'm catching it, I have to slow it down. And so how do the two forces of my hand on the ball compare to when it's slowing down? Is that equal? Or is it greater than? Or is it less than the force when it's just at rest? I'll give you guys a top hat question on that. Give you a bit of time to answer that. Let's do it like this. Ask you for a big favor. Could you please fill this one? You guys okay to click in about 30 seconds? Check your neighbor. Okay, going once, going twice. Okay. The survey says, thank you so much. Appreciate it. Just see if I... Ooh, it's kind of split. Either the same or the catching force is greater than. So this could be an interpretation thing. I liked, for the full 1 point, remember everybody gets 0.8 for these, that what's happening, I think, is that if it's at rest, then, so in both cases, it's the same force diagram, right? Which is the force of your hand on the ball, and there's the mg acting down. So at rest, acceleration equals 0, and while catching, it's the ball is slowing down. And it's moving down. So if it's coming down and it's slowing down, which way is the acceleration? It's like opposite the velocity, right? So my thinking is that while you're catching it, there is some upward acceleration, is up. So instead of balancing the force of the hand on the ball with gravity, the force of the hand on the ball has to be greater than the gravity while you're catching it in order to slow it down. So what I do is I draw a force diagram to show what all the forces are, and then I think also about the acceleration. Sometimes you know that the acceleration is 0 because it says something about constant velocity, or it's at rest or something. And sometimes you know that it's accelerating, as you've been told. And if it is accelerating, you want to not balance the forces, and if it's 0 acceleration, you want to balance them. Let's work through an example, shall we? Since we're here, since we're all getting ready for things, tests. 3 blocks are being accelerated upward at 3 meters per second squared by some force. So again, it's drawn right here on a kind of a sketch, which is good. So I'm going to draw a force diagram on something, but every time I do that, we're going to make sure that things are unbalanced and there's a upward force, net, sum of all the forces. Mass of the bottom block is 7 kilograms. The mass of the middle block is 14 kilograms, so 2m. And the mass of the top block is 21 kilograms, so that's 3m. Find the magnitude of F. So, this is now an external force. So what I'm going to do is I'm going to draw my little dashed line around all of them. Let's just define, since I'm trying to find an external force here, let's define the system equals all 3 blocks. And you may not know to do this, but I think it's something that comes with a bit of practice. I've been asked for this force, which is external. It's acting on the bottom block, but they're all kind of connected. So I should be able to find this. This is very similar to the quiz question, actually. And I know that a sub y is plus 3.2. And the mass of the system is just equal to 7 plus 14 plus 21. I think it's 42 kilograms. Okay. And I need to find F. So, diagram just looks like this. You've got F, and you've got M, I guess, of the system times G acting down, the gravity force. And the idea here is that once I've defined a system, the internal forces between all the blocks do not go on a force diagram. You only draw external forces from other objects. So there is some external pushing force, F, and then gravity is an external force as well, right? Because it's coming from the Earth. And that's it. There's no other forces to draw. So we're done. All we have to do now is do Newton's second law. It's our next step. Some people write F equals MA, that's fine. I find the book tends to write A equals F over M, whatever, same thing. But again, the F is going to be the vector sum of all your forces. And don't forget to define, let's define plus y equals up, so that the gravity force is going to be subtracted. So it's just F minus mass of the system times G. I'll divide it by the mass of the system. Sorry, I guess I should put that on here. And then just solve for F. I think I get something like F equals, I'll go through the math a little quickly here, mass of the system times A sub y. It's the same sort of math that we did on the pre-class quiz. So 42 times 3.2 plus, that's a plus I think, 42 times 9.8. And when I typed that all in, I got 546 newtons. I guess I could round that to two significant figures if I want to. Rounded to two sig figs. How are we doing? Guys are good? Okay. The other question you might be asked in something like this is, just see here, is something about one of these middle blocks. So let's do same question, but now I want to say, all right, 3 blocks accelerating upward. These are the masses. What is the magnitude of the normal force that the top block exerts on the middle block? So my trick here is to keep things simple. I'm going to set 1 is the top, 2 is the middle, and 3 is the bottom. And what we need is the normal force of 1 on 2. That's what you're asked for. But that's going to be kind of hard since it's squashed in the middle here. So by Newton's third law, the magnitude of the normal force of 1 on 2 equals the magnitude of the normal force of 2 on 1. And that'll be a bit easier. So let's find this. And then all I have to do is define the system as the top block, and then it's really easy. So define the system equals this block 1. And so then it's just the normal force of 2 on 1. You got the same, and the normal and the mass of 1 times g downwards. So I'll just say that a sub y equals the sum of those two forces divided by m1, and I get n2 on 1 minus m1 times g is equal to m1 times a sub y. N2 on 1 equals the mass of 1 times a sub y plus g. So I get 21 kilograms times 9.8 plus 3.2. I think I got 270 newtons. And since that's the magnitude of 1 on 2, it should also be the magnitude of the of 2 on 1. Sorry, that's also the magnitude of 2 on 1. One on 2. Okay. All right. Got another, let's do this, I guess. Let's do the demo. So I'll make a top hat question for this. Jonathan has set up a very cool demonstration in which there's a spring scale in the middle and there's two masses on either side. So let's move some of this stuff off. And you're asked to find what is the scale reading in the middle. And they've said that they're 100 Newton weights. What weights do you actually have? 200 grams. So 0.2 kilograms, so it's a bit different. But anyway, this scale, what does it read? It reads grams, so that's good. So we're going to try to, do you want to try to hook it up? All right, if you try to hook it up, I will first switch to here. How are you going to have the video on it, by the way?
So I think...
Do you want me to hold this one? Okay.
The tape is there so you can see the white numbers just a little bit better.
Okay.
It doesn't show perfectly. Maybe I'll try to adjust the camera.
Put that down a little, make it a little more horizontal. Okay. Awesome. Should we give you guys a little time to... I'm a little curious to see what people are thinking here. If you disagree with your neighbor, please convince your neighbor that you're correct. And it's not going to be my opinion. We're going to just check it in real life.
You think we're going to be able to do it, but you should switch or something? Oh, it's the input that now is supposed to work. So this guy right here, which is
10 seconds.
Which one is that? I think it must be.
Yeah. Nice.
Okay, so when we're ready, you can just...
Okay. First, I want to see the prediction, then we'll see what Jonathan's got. Wow. It's all the heck over the place. Let's take a look at the video. So it's not zero. I don't know if you guys can see it. It's a little hard to see, but it is now hanging. You can sort of see the notch. It's sitting right there around 200. Actually, it looks more like maybe 180 on here. It's pretty close to 200, which is, by the way, the mass of both of these. If I look over here, that's a 200-gram mass. Look over there, it's a 200-gram mass. And it kind of makes sense, I think. If I was to hold just a 200-gram mass, maybe take off the other one or something, it wasn't even there. This wasn't here, but I was just holding it. Still, 200 grams. Makes some sense, right? I'm supporting 200 grams. The fact that I put another 200 grams on there doesn't really change it. It just makes it not fall. If I let go of this falls. But when they hang that over the edge. So, it's sort of the nature of tension. This spring measures the tension in either rope. And then, so when you've got it there. So the answer I was looking for is B, I think. Let's go back to here. So thank you. Thanks very much for that. Is that making sense? What do you guys think? You got any questions about that? Yep. What are you thinking?
What would the force diagram of that look like?
Well, that's a great question. So in order to draw a force diagram, you need an object. So if you pick this mass, then there's a tension force up and gravity. So certainly the tension right here is going to be 100 newtons because that's what's needed to support it from gravity. So it's not accelerating. And then the idea with pulleys is that you keep the same tension on both sides of a pulley. So it's 100 newtons here. And again, there's a force diagram over here. Pulling up, that's got to be 100 newtons. So that tension has to be 100 newtons, and that's exactly what the spring scale in the middle measures. It just measures the tension in the string. Okay, that's what springs do. All right. Not an easy one, but I guess I could put it on here, is that this is like going to be 100 newtons tension up. T is equal to that. And then I'll say that tension is the same on both sides of the pulley. And so the scale reads the tension on either side. Okay. So I've got another top hat question for you, but first let's go through a little overview. I want to do a little table of forces of 1 on 2 and some examples. So I'll give you some objects. For example, gravity. Well, gravity is always the Earth acting on something. And this is the symbol. A lot of textbooks put F sub g or something, which is fine, but it's always mg. There's an equation for gravity. It's the mass of object 2, I guess, times 9.8. So tension, there's a rope, I guess, and then the object is tied to a rope usually. And so you call it, Atkina puts a capital T. So that's a force in newtons that we use capital T for. And then it's the rope acting on the object. And there's no equation for tension. You have to kind of find it from the situation. Such as, if I know that there's a rope attached to a hanging mass, and it's not accelerating, then I can use Newton's second law or something, balance it out. Say that this upward force has to cancel the downward force mg, and you're going to end up solving that the tension, I think, is equal to mg, probably. But it's not because we know an equation for tension, it's just because of Newton's second law. And then normal force, you've got a surface and an object. She uses a capital N for that force in newtons, S on O, surface on the object. And again, this is one of these as-needed forces. You solve Newton's second law to find the normal force. There's no equation for it. And then static friction is the same thing, but its normal force is perpendicular to the surface on the object. It's that component. And static friction force is parallel to the surface. It's that component. But they're both as needed. There's no equations for friction or normal or tension. Sorry, static friction or normal or tension. And then there's kinetic friction, which is like static friction, except there's an equation, which is mu times the normal force. And it slows the thing down. Okay. Let's do another top hat. So here we have 3 different forces being applied to the same crate in 3 different situations. And actually, in the first 2 situations, the crate's just sitting there, not moving. She's not giving it enough force. But then, I guess she gets it going, but then it's sliding at constant velocity. V equals 1 meter per second. So it's still not accelerating, even in case C, I think. It's moving, but not accelerating, if that makes sense. And in the first 2 cases, A and B, it's not even moving, so it's also not accelerating. So the question is, in which case is the magnitude of the friction force of the floor on the crate the greatest? A, B, C, or, oh, that's wrong. Should say, actually, let's just go to this actual laptop here. It's right on the top hat, and it was wrong on the screen, so I'll change it. It's the magnitude, D is the magnitude of the friction force of the floor in the crate is the same in all 3 cases. can see it a little better there. So check your neighbor. Maybe vote in. You got about 45 seconds. Ten seconds, 5 seconds. Okay. Let's see what the survey says. And then I'll tell you what I think. So it's sort of split. A lot of people are voting for C. So what I was doing is I was just drawing the force diagram of the crate. And so I think this is the force of friction. I think it's actually a force of, it's the surface on the crate. It could be static or it could be kinetic. But in all cases, if acceleration is 0 in all cases, then I think you have to balance all these forces. So the normal force of the surface on the crate is equal to m of the crate on g. These are to balance the y forces. So balance the y forces. So it's not accelerating up or down. And then if you balance the x forces, x components of the forces, you'll get the force of friction of the surface on the crate is equal to the force of pushing on the crate. Okay, so it's biggest here. Make sense? Yep, sorry. Was my... Oh. Sure, let's ask about the spring. What do you think about the spring?
So I was just wondering about the spring.
Yeah.
If it had another spring attachment attached to the other 100 newtons, then would it have been 0? Because that's kind of the scenario I was thinking.
If you had 2 spring scales?
No, but in one. Because I thought that you were attaching 100 newtons to each end of the, a double-sided one. If it was double-sided.
A double-sided spring scale?
Yeah.
Well, this already is double-sided. This spring scale is the top and the bottom of it. It's attached here and it's attached here. I think we'll have to talk after class. You should come and look at it after the class. So, are we good with the crates one? I'll come back to you with that question. Okay. We got one more question. I'm glad you guys are all still here at 11:58. I really appreciate it. Bob stands under a low concrete arch and presses upward on it with a force of 100 newtons. And there's already a downward force of gravity of 800 newtons on Bob. So, what's the force of the normal force of the ground on Bob? So if he was standing on a scale or something. So I'm going to draw the force diagram, and you can try to pick. But you've got the force of the ground on Bob. That's what you're trying to find. And then there's the force of the arch on Bob. It's pushing downward, I think. So if he's pushing upward with 100 newtons, this is equal to the force of Bob on arch. By Newton's third law, this should be the force of the arch on Bob. And then there's another force, also downwards, of the mass of Bob times g. And the acceleration is 0. I'm not moving up or down. Alrighty. I'll let you guys ponder that a little bit. We are pretty much done. I might do a couple more examples from chapter 3 next time, but then I'm going to get into chapter 4 stuff, in which we we go into 2D. We're not going to go into 3D this semester. So, all right. I'll see you on, whatever today is, on Wednesday.